Alright, let's take a look at number 18. We just got done solving a rational equation. Now we'll solve a radical equation. So we got our variable showing up inside the square root in this problem. So we got a variable in the radical. With that said, we're going to have to figure out how to get it out of there. So with the radical equation, your first step is to isolate the radical term. So there's two words you want to remember when you're solving radicals, and that's to isolate, eliminate. Isolate and eliminate in that order. So as we got this equation, right, we got 7 plus the square root of x plus 13 equal to x. We got to get that square root term by itself, right? So we want to isolate this term. So let's go ahead and subtract the 7 over to the other side of the equation, right? And then we can isolate it. So with that, we have what? The square root of x plus 13 equal to x minus 7, right, as we isolate that. So again, you want to get that by itself. So we've done that, right? We've solved for or isolated the square root term. Now that we've isolated it, we're ready to eliminate it. That's your second step. So step 2 is your elimination step. And how do you eliminate a square root? You're going to square it. So we're going to use the principle of powers, and we're going to raise both sides to a power of 2. So whatever the index of your root is, we're going to raise it that power to eliminate it. So if it's a cube root, we would cube it. The fourth root, raise it to fourth power. Square root, we want to square it. And just remember, you're squaring the entire side. And if we square the square root of x plus 13, that'll eliminate square root and leaves us with x plus 13. And be careful on the right side. We're squaring a binomial. We're squaring x minus 7. So that's x minus 7 times x minus 7. So let's go ahead and distribute and square that. So be careful on the right side. All right, we do need to square this out. So that's x squared minus 7x. As we distribute the negative 7 through, we end up with negative 7x plus 49. And as we combine our like terms, we end up simplifying down to x plus 13 equal to x squared minus 14x plus 49. So here's our resulting equation. All right, so after we eliminate, we got a new equation to work with. Right, an equation without a radical in it. And that was our goal. Right, so we end up with a quadratic, right, equation. So we've got a quadratic equation, and we all know how to solve a quadratic. We're going to set it equal to 0. So that's our next step, right? So our next step, right, is to set equal to 0, and then try to factor or use a quadratic formula, right, how we're going to go with that. So let's go ahead and do that. Let's get all the terms on one side, move everything to the right side. So I'll go ahead and subtract the x, subtract the 13. As we do that, right, what do we end up with our equation? So that implies what? 0 equals x squared minus 15x plus 36. Well, they gave us something that we can easily factor. So I'm going to go ahead and factor this quadratic. So we know with this quadratic right here, we've got two linear factors. We'll go ahead and produce those. We need an x and x up front. What factors of 36 combine together to make 15? Well, we know 3 and 12 do. So we're going to need a minus 3 and a minus 12. And then we can apply our zero factor property. We know x minus 3 can equal 0, or x minus 12 can equal 0. As we solve for x, as we add those over, we get x equal to 3, or x equal to 12. Now we got to make sure that we check. So we have the possibility of what we call extraneous solutions. So let's check our answers. So as we check, all right, let's start with 3. So x equals 3, as we plug that in, that would be 7 plus the square root of 3 plus 13 equal to 3. So out went x and went 3. Well, that's 7 plus square root of 16 equal to 3, which is 7 plus 4 equal to 3, which is 11 equal to 3. Well, it doesn't check, right? So that means what? That means this is a extraneous solution, assuming our work is correct. So x equals 3 is not a solution. Now let's check the other one. Let's check x equal to what? 12. So with x equals 12, we get 7 plus the square root of 12 plus 13 equal to 12. As we simplify that down, we get 7 plus the square root of 25 equal to 12, which is 7 plus 5 equal to 12, which is true, 12 equal to 12. It checks. Right, so we have one extraneous solution. So again, that's an extraneous solution. All right, so we only have one answer. So our only answer is x equal to 12. So D. D will be your answer choice. Be careful, you see, answer choice C be a common mistake. So 3 does not check. So of the two, only one of them will work. So just make sure you check those. All right, so again, that's solving radicals. Isolate and eliminate. So we're solving those down. Let's move on. Let's look at our next problem. We've got an absolute value equation. All right, solving absolute value equations. We solve them just like we would a linear inequality, linear equation. We just got to use our properties, all right? Because as we look at this, we got to use our definition of what it means to be an absolute value. So remember, absolute values. Let's put our absolute value definition up here. All right, so I'll write that up here at the top. Absolute value definition. We're going to apply that. We know the absolute value of x equals some number a. Right, assuming a is greater than or equal to 0. That implies x equal negative a or x equal a. All right, so we're going to apply that. So we're going to solve for x, right? And we got a greater than problem, right? So we're going to apply the definition. All right, so apply the absolute value definition. So that implies 3x minus 1 over 4. Now, here's where we got to be careful. When we introduce negative 8, so we know absolute value is going to equal 8 and be negative 8 or 8. So we got to look at flipping when we use the negative. So that's because the negative got to reverse the inequality symbol. Or we got 3x minus 1 over 4 greater than 8. So just be careful with that. With a greater than problem, it's a or problem. So again, we set up, so we got to flip with the negative. So again, make sure you flip it. So you flip, all right, with the negative. So we'll make that note. So now, like I said, we're solving two linear inequalities. So as we're going to solve these, it might help. We won't. We'll go ahead and clear out the fraction. So let's go ahead and times both sides by 4. So we can go ahead and clear those out. All right, as we do that, right, we simplify it nice. So we get 3x minus 1. Now we did multiply by negative 4 is a positive, so it stays a negative or less than. And over here, as we multiply both sides by 4, we get 3x minus 1 greater than 32. And as we solve for x, we'll go ahead and add the 1 over both sides. So that gives us, what, 3x less than negative 31. And over here, we get 3x greater than 33. And then we'll divide out our coefficient, and then we'll have what x is. So as we divide out the 3 on both sides, all right, what do we come up with? We come up with our answer, our solution set. X is going to have to be less than negative 31 thirds, or x is going to have to be greater than 11. So with that said, if you want to look at that, it might help you graph it. Let's graph the solution set. So let's put negative 31 thirds on here. And that's what, negative 10 and 1/3. And let's put 11 on here. So less than negative 31 thirds. It's all these numbers, right, all the way to negative infinity. Or greater than 11. It's all these to positive infinity. So as an interval goes, right, our preferred form, negative infinity to negative 31 thirds, parentheses, or all values greater than 11, which is the interval parentheses 11 to infinity. So you see your solution set, right, and that's answer choice D here. Less than negative 31 thirds or greater than 11. Right, so answer choice D on that one. So solving a absolute value inequality, so apply your absolute value definition. Equal negative A or A, right, when we equal A. Set up your two inequalities with that. So again, that would be negative 8 or 8 inside here. So with it being greater than 8. All right, let's go down here to rational graphs. Moving on, let's find the domain, holes, asymptotes, intercepts for the given rational. So this helps us in sketching a graph of a rational function. Now your first step in dealing with rationals is make sure that you simplify your fractions by factoring. So anywhere to factor, go ahead and do that. So we have a quadratic denominator. So let's go ahead and factor that down. We need an x and an x up front for the x squared term. Right? We know that our constant term of 4, right? We know the factors of 4 are going to work together. We need a minus 4 and a plus 1. So x minus 4 and x plus 1, right? We will get x squared minus 3x minus 4 back. So we distribute that out. Now nothing reduces, nothing cancels out in that. So with that said, we're ready to go to define our information. So holes, we'll start off with description of holes. Your graph has a hole, and that means a point of discontinuity, an ordered pair which our graph breaks or jumps over. All right, holes come from common factors. So the holes come from the zeros of your common factors. That's the algebra behind it. All right, so in this, right, this example, we have no holes, right? There's no common factors to talk about. Nothing divided out in this rational, so there are none. So there's no points of discontinuity, right? No ordered pairs which our graph breaks. Now, as we continue our topic of breaks in our graph, we got to move on to asymptotes, and that's where we talk about vertical asymptotes. Vertical asymptotes also talk about undefined values. All right, vertical asymptotes come into play from looking at the zeros of your denominator factors. So now we've already factored, right? What are the zeros of our denominator, right? X minus 4 equals 0, or x plus 1 equals 0. So x can equal 4, or x can equal negative 1. So we got 4 and negative 1 are our zeros. So that means our vertical asymptotes are x equal to negative 1, right? And x equal to 4. So we have two of them, two vertical asymptotes. And remember, asymptotes are equations of vertical lines that shape our graph. So if we look at this graph, and you can go ahead and start talking about it, right? And this leads you to your domain. So if you're going to graph in this function, right, at negative 1 and at 4 on the x-axis, right, you would have these asymptotes, which is where your graph would go vertical. These are those two vertical asymptotes. So these are undefined values. So our domain will be, our graph will take place to the left and the middle to the right. So with that said, we can go right to the domain, which they've asked us to find. So domain will be all real numbers less than negative 1, or all the numbers greater than -1 and less than 4, or all the numbers greater than 4. There's your domain. All real number values of x that satisfy our function. -1 and 4 don't. They're the zeros of our denominators. Right? Those are undefined values. So just remember, your undefined values, right, produce, in this example, produce your vertical asymptotes. Of course, we'd also have an undefined value if we had a hole, which we'd have to exclude, but we didn't have one. So that will lead you to domain once you found your holes and vertical asymptotes. Now, we also have the topic of a horizontal asymptote to look for. All right, and a horizontal asymptote is an equation of a horizontal line that'll shape your graph. So vertical asymptotes, vertical lines shape your graph will go vertical at those locations. Horizontal asymptote will take place when you have a horizontal line, right, which you'll find out if you have a horizontal line that shapes your graph by comparing the degrees. Compare the degrees of the numerator and denominator polynomial. So if we let n, we'll let n be the numerator degree. All right, and that problem is a degree 1 linear. And we'll let m be the denominator degree. All right, and denominator degree is 2. So as we compare these, we have n being less than m. So if n is less than m, that implies a horizontal asymptote exists. And it exists at the line y equal to 0. Anytime n is less than m, your x-axis is going to be a horizontal asymptote. So up here at your graph, in here, this line here, y equal to 0, that would be a horizontal. So your graph will flatten out there at the x-axis. Right, as it goes infinity, negative infinity, you'll see that characteristic take place. You can graph it and sketch it here in a little bit. So n less than m, y equals 0, your horizontal. Now moving on, let's get some quick points. How about finding x-intercepts? All right, x-intercepts, right, are when our function equals 0, right? So when does f of x equal 0? That's the example. So in a rational function, right, that implies this. When does x minus 1 over x minus 4 times x plus 1 equal 0? Well, that means when does our numerator equal 0? So if we solve for x, right, we would add the 1 over, and we get x equal 1, and that's your x-intercept. So our x-intercept will be the ordered pair 1, 0. So again, that's a point of intersection with our graph, right, with the x-axis. So x-intercepts are always located by the zeros of your numerator polynomial after you reduced it. So again, when does your function equal 0? Now how about your y-intercept? So how would you find the y-intercept point? Well, another quick point you can determine, right? Y-intercept point is what does f of 0 equal? Right? Y-intercept, you let x equal 0. So that implies what? What is f of 0? Well, that would be equal to 0 minus 1 divided by 0 squared minus 3 times 0 minus 4. As we simplify that, we end up with -1 over -4, which is 1/4. So there's your y-intercept. It would be that ordered pair, 0, 1/4. So that's where our graph will cross through the y-axis. So at this point, you could graph it, right? You could check it. So now you could get a quick picture just to see those characteristics, right? You could look at it there on your grapher in your TI calculator, right, to find those pieces of information. So again, this would be a good place to graph it, to check it, to look at it. So you can take that time and sketch it. All right. So if you want, let's pull up our calculator. All right. Now I'm gonna go ahead and I'm going to do it here on the Desmos calculator, and we get a little better picture than the TI one I have. But we can do it on both. But let's put in here our given function. So I'm going to store in here x minus 1. All right, let's see if we can type it in here correctly. Maybe we should put that in parentheses. So x minus 1, close that, divided by our denominator. We had what? X squared. All right, and we have what? Minus 3x minus 4. All right, there was our graph. Now as you look here on your graph, right, there's that x-intercept of 1, 0. There's that y-intercept of 0, 1, 4. And you can see your graph flattening out at the x-axis. It goes infinity, negative infinity. And you can see it going vertical, right here at -1 and at 4 on the x-axis. So again, you can always do a quick check of that information. And again, if you have your TI, we can put in our TI also. Let's see what it looks like here on TI. X minus 1 divided by x squared minus 3x minus 4. So again, closing out the denominator. But then graphing that, you get an okay picture here. And you go to your table, right, and you see your errors. What? Got an error at -1. Got an error at 4. Domain was all real numbers except -1 or 4. Right? Those were those two undefined values. So all the values except those two. So you got your grapher there. You can check them. Now moving on, let's go to number 21. Now number 21, our first step, let's go ahead and see if we can reduce this fraction. X squared plus 2x minus 3. Well, that has two linear factors. Need an x and x up front. We know plus 3 and minus 1. They are factors of 3. They'll combine together to make 2. That middle term coefficient. But again, you can distribute that. Get x squared plus 2x minus 3 back. So we factor the denominator. We need x and x up front for the x squared term. What factors of 6 make the middle term coefficient of 1? We're going to need a plus 3 and a minus 2 to make that happen. And you notice what happens in this one. So this time, as we look at this one, we have a rational that reduces. We end up getting x minus 1 over x minus 2. So when we lead to the conversation of holes in our graph, remember the holes are the zeros of your common factors, which this one has. So remember our common factor, we had a common factor of x plus 3 in this example. So what is it? 0, x equal -3. Now you want to go ahead and find what y equal. So to find y, right, we're going to plug that in. So that'll be f of -3, which is -3 minus 1 over -3 minus 2, which is -4 over -5, or 4/5. So y is equal to 4/5. So our whole, there's our whole. So our 0 of our common factor was -3, and it produced an output of 4/5. So -3 4/5 would be the whole in this graph, that ordered pair. So -3.8, you're going to see your graph jump over that point. That's a point of discontinuity and undefined value, and that'll tell us a little bit about our domain too. It's a value we're going to exclude from the domain, -3. Moving on, let's go to the vertical asymptotes. And remember, to find the vertical asymptotes, we look at the zeros of the remaining denominator factors. Now, because this one we have reduced, right? Our only denominator factor is x minus 2. We divided out the x plus 3. And that gives us what? X equal to 2. So the 0 is 2, so that implies x equal to 2, right, is our vertical asymptotes. We only have one. So our graph will go vertical at that location. So if you look at this graph, if you wanted to do a quick sketch just to see visually what would happen on this graph. So over here at 2, you'd have the graph going vertical, getting closer and closer and closer to this line. We'll never touch it. It's an undefined value. And then at -3 4/5, you would have a hole, an ordered pair which your graph jumps over. So an undefined value. So as far as domain goes, our domain, and we'll make note of that, all real numbers except -3 or 2. So let's go ahead and write out domain in interval notation. So listing all the x values. So all real numbers less than -3, right? Or all the numbers greater than -3 and less than 2. So left of the hole, right of the hole, and left of the vertical asymptote, and then to the right of the vertical. There's your domain, right? There's the domain of this rational function. All right, now let's move on. So now we talked about vertical asymptotes and holes. We've gone over the undefined values. As we move to the horizontal asymptote, is there a horizontal line that will shape this graph? In our last problem, it was the x-axis, line y equals 0, because degree of numerator is less than degree of denominator. So let's compare the degrees. All right, so remember, as we compare the degrees, all right, we're looking at the numerator degree, so we'll let n, again, be the numerator degree. And then this example, we have a quadratic, and m, let that be the denominator degree. And our denominator degree is also 2. So as we compare these two, this time they're equal. Well, if n is less than or equal to m, our horizontal asymptote exists. Now, if n is greater than m, there is no horizontal asymptote. Now, where will it exist? When you have degrees being the same, you're going to look back at the leading coefficients, right, for this problem. So find your leading coefficients in the example. So we have a coefficient of 1 and 1, right, in this one. So y going to 1. So these are the degrees, right, or I'm sorry, the leading coefficients, right? So you divide the leading coefficients. Right? So 1 over 1. So that implies y equal 1. So we had a 1x squared and a 1x squared in the denominator. Those are the leading terms. Leading coefficients were both 1. So it'll flatten out. Yeah, y equal to 1. That's your horizontal asymptote. All right. With that said, only left to get our intercepts. Let's find out where this graph would cross the x-axis soon as an x-intercept. So remember, we're going to find that by taking our function and setting it equals 0, which means when does x minus 1 over x minus 2 equal 0? So that implies when does x minus 1 equal 0? So that implies x equal 1. So we'll have an x-intercept at 1, 0. And our y-intercept, so let's go ahead and find it. Where will the graph cross through the y-axis? And remember, to find a y-intercept, we're going to find out what f of 0 equals. So f of 0 is equal to 0 minus 1 divided by 0 minus 2, which is -1 over -2, or 1/2. Right? So our y-intercept will be at 0, 1/2. Right? So again, there's our graph. Now you check it and graph it, sketch it, look at it there on your TI, see information. Take the time and do that and graph it just to look at it with the function. But I hope that helps you with asymptotes. So we'll take a break and continue on.